Thank you, Jason. Thank you, Alec. So, hello, my name is Shalom. I'm from Outbrain. Today I'm going to talk about Outbrain case study with Scylla. It will be together with Shlomi, VP R&D of Scylla. So, I'm going to talk how did we manage to lower latency while doing 20 times more operations of Cassandra. So, a little bit about me. My name is Shalom, as I said, from Israel, from Outbrain. I work for the recommendations group. Production engineer is like a dedicated DevOps for R&D group. I was also a member of data operations team, who was in charge of Cassandra, Elasticsearch, MySQL, Redis, and more. Also was a DevOps engineer at Everything Me. The team was in charge of ETL, Chef, cookbooks, monitoring, infrastructure, automation, and on and on and on. So, a little bit about Outbrain. Outbrain is the world's largest content discovery platform. We have 500 million unique visitors per month. We are serving 250 billion personalized content recommendations every month also. And you can see our customer is ESPN, CNN, Le Monde, and on and on and on. So how does it look? This is a web page from CNN. As you can see here, this is the Outbrain widget. Also, is appearing here. Every recommendation called also document or article, and this is what I'm going to talk about. So, a little bit about the infrastructure at Outbrain. We have 3 data centers, all of them here in the US. We have 7,000 servers. It's our data centers, physical hardware. 2,000 of them is data servers, including Hadoop, Cassandra, Elasticsearch, Scylla, and on. We are storing petabytes of data. And we also have real hardcore open source DevOps shops. You can log on to our GitHub page and look what we have. So, Cassandra at Outbrain. We have 16 Cassandra clusters, total of something like about 400 nodes. I'm going to talk about the document services Cassandra. About this cluster, you can see the spec, memory disks, and Ethernet. And the most important, we are working today with Cassandra 2.1 with DataStax package. So, what is the use case? How do we store the data in this cluster? So we are holding the data in a key value manner. We have less or more 2 billion records. We have 10 nodes in each DC, so 3 data centers, total of 30 nodes. And we were working with replication factor of 3 and local quorum for writes and reads. What is the usage? Okay, so we are serving our documents, which, as I said before, called article or recommendation, for different flows. 50,000 writes per minute, 2 to 3 million reads per minute per each DC, and we are growing. The SLA. So we must apply a single request in 10 milliseconds. I'm talking about the 99th percentile. And there is also multi-request. The SLA is 200 milliseconds, also 99th percentile. Multi-request is, instead of doing one big query, we are splitting it to multi-small queries, and we're measuring it by the slowest query. So, the cluster is the same for offline processes and serving use cases. What does it mean? Offline process can be like, I'm crawling a web page, and I'm putting it in the Cassandra with doc ID and stuff. So this is an offline process. The serving process is when someone is entering, I don't know, a CNN web page, and the widget is rendering online. And it goes through microservices. The serving application doesn't call the Cassandra, it's called the Document Services API, which call the Cassandra, retrieve the data, and everyone happy. So, we deployed Cassandra. How did we deploy it? We deployed Cassandra only, no Memcache. So as you can see here, this is the serving applications called the Document Services API. Read from Cassandra, retrieve the data. Nice. So it scales up to 1.5 million requests reads per minute with local quorum, which if the replication factor is 3, so it doubled the request to 3 million. And we have quick writes, 99th percentile is up to 5 milliseconds. but slow reads, 50 milliseconds in the 99th percentile, no good, SLA is 10. So what issues we had with version 1? There is the consistency versus performance. What does it mean? If we choose local 1 consistency, we are getting weak consistency, but we are getting a lower latency. Good, not good, I will decide. And if I choose local quorum, it's stronger consistency, but the performance is a little bit lower. But I want to have the stronger consistency because I want to supply the updated data, the best data, because I want to serve the best recommendations that I can for you to click about it. That's it. And also, we had the problem that scale growing versus performance. If we scale, performance will be not good at all, and that's it. So what did we do to solve it? We deployed a Memcache. So we deployed in each DC Memcache DC local cluster on top of Cassandra, 15 minutes TTL. And the flow is, there is also, again, serving application called the microservice. And he asks, get from the Memcache the data. If a success, nice, go back. If not, you fall back to Cassandra, read from Cassandra. And with this read, he does 2 things. 1, he retrieves the data to the serving application. 2, store it in Memcache. And after we did this, reads volume from Cassandra were like 500,000 reads per minute. Now there is within the SLA, which now it's 5 milliseconds in the 99th percentile. So what issues did we have or still having? Stale data from cache. How do we fill up the Memcache? If I write to Cassandra, it's only write to Cassandra. It's not fill up the Memcache. It's no good. When I fill up the Memcache, when I get a miss, then I read from Cassandra and I write it to the Memcache. So in 15 minutes, the data can change, but I cannot update it, and it's not good. Also, a complex solution, more moving parts. I'm wasting more servers for the Memcache. Not the best for us. And also the cold cache. If we're purging the Memcache, so Cassandra gets full volume. And I can tell you that one time we traffic shift, we shift our traffic from DC1 to DC2. We purge all the cache in the Memcache in DC1. And when we shift the traffic back, our Cassandra just rebooted because it cannot handle the load. Well, it's good, but not good enough. And then Scylla came along, and Shlomi will talk about this part also.
So we deployed a 30-node cluster, 10 nodes in each DC, parallel to Cassandra. And the write microservice was updated. So writes are done parallel, one to Cassandra and one to Scylla. The read process was changed, so a read would hit Scylla or would hit Memcache, and if there was no data, it would hit Cassandra. The fact that we used 30 nodes and replicated Cassandra allowed us to do a trick to upload the data fast. So what we did is we transferred the token ownership and made a one-to-one node mapping between Cassandra and Scylla. We did that by copying the system tables and then booting up the cluster. This meant that each node retained its tokens and then updated its IPs. After we had the cluster running, we enabled dual writes. And once dual writes were enabled, we could take a snapshot from the Cassandra, transfer the files, and load them. So we didn't need to stream in all the data. We could just copy it and then use refresh to upload all the data. Comparison, once the data was up and we had all the data in Scylla, we could do a difference and validate that Scylla was actually returning the same data as Cassandra. Now, the small trick here was that Cassandra was using Memcache, and some of the data in the Memcache was stale. So we could do comparison only for data returned from Cassandra. Along the way, we've learned a lot of things. I'm going to cover 4 items. They're relevant to Cassandra and Scylla as well. The first item that we tackled was Bursty clients. Now, once we had all the data, we saw that at specific intervals, every 5 minutes, there was a spike of timeouts in the read client. We tried to search what was the reason, and one of the items that, of course, we checked was the network saturated? The metrics that we used were in 1 minute. And when looking at 1 minute intervals, it seems that everything was OK. We were using 10 megabytes per second, and the network was 1 gigabyte. But after eliminating a lot of stuff, we found that looking in finer grained, using a simple script, there was an issue of burst hitting. So there were clients that were sending a lot of SQL requests in sub-second intervals. And that, of course, caused an issue because we couldn't return the result. We were saturating the network. This was alleviated on Outbrain side by updating the applications to disperse their requests so they won't hit us, or Cassandra, for that case, instantaneously with all the traffic. One other item that we looked at is how much are we reading off the disk to serve a query. So in this cluster, they're using leveled compaction. Usually a query that is not in memory is returned by a single read off the disk. And we saw that looking at the stats, we're reading around 27 kilobytes and returning only to the client 4 kilobytes back. So there is a big discrepancy, and we're reading a lot of data and throwing it away. We found that using nodal CF stats, we saw that the largest partition size in this cluster was 4K, so we updated the chunk size from 64K, which was the default, to 4K. And that allows us to remove a lot of the additional data reads. After removing the issue of seeing the spikes every 5 minutes, everything seems to be OK, yet in some cases, there was latencies of more than 100 milliseconds. And if the cluster is returning under 10 milliseconds, most of the traffic, and at times more than 100 milliseconds, it seems that it was related to cross-DC. But we're doing local quorum reads. How can that be? So let's look first at what does it mean when we're doing global read repair. And the issue was global read repair. So a client sending a request to a local DC, when you have global read repair, it will actually force you to send a read to all the replicas. And the coordinator in your local DC will send reads to the remote DC nodes. The data that is returned from the local nodes, local replicas, if it's the same, then the result will be returned back. And the process of doing the data comparisons from the remote nodes is done in the background. But what happens when the data is not the same in the local DC? So when the data is not the same, we start again. We're sending a request to the remote DC. We found out that the local data is different, and then we simply need to wait. We need to wait for all the replicas to return the result in order to consolidate, find what is the difference, update the remote nodes, and only then return the result. So although you're using local quorum, which sounds great, you can get into a situation where you have cross-DC latencies. And in Outbrain case, this was apparent more than what we expected. So the issue there was that they were doing read after write. So there was a process that was actually writing with local quorum, and they have 3 nodes in the local DC. So it would return after writing to 2 nodes. And then there was immediate read that would hit a different node in the local DC, a different coordinator node. So it would read its local data, one of the replicas that was already updated, and then see that there was a difference. So a read after write can cause this. So this is a bit chunk, but I'll try to cover it. So we have the read request from the client hitting the coordinator. Then we send reads to the local nodes and the remote nodes. We find that we get the result and find that the results are different. Now in Scylla, what we use a timestamp of the data that we read back and the timestamp of the read operation. We find those are with very little delta. And in this case, we find that there is a read after write and fall back to doing a local read repair. So instead of waiting, for the remote replicas to return the result, we use the local replicas information, compute, and do the diff, write the diffs through the local nodes, receive an acknowledgement, and then return the result. This is applicable from 1.3. Last, the notorious cold cache. When we're starting a node, we actually need to serve all the information off the disk. What happens if we're starting a node at peak traffic? We're actually bottlenecked by the disk. Now, the solution in Cassandra to solve this is to use dynamic snitch. Dynamic snitch allows a node to basically monitor the latencies coming from replicas and then disperse the information based on those latencies. Now, it's OK, but it looks at the queries and thinks that everything is the same. So it can have key space and column family distinction, but all the queries to the column family are the same from its standpoint. In Scylla, we are trying to do this in a more fine-grained manner. So we're working to look at the cache hit ratio and be able to do it in a prepared statement level as well. So after explaining everything, we want to see some numbers. So, OK, I think I'll skip this one and talk about this one. So the slides are the same. I'll just go back. This is just, the next slide is a focus on this slide. So what do we have here? So this is Scylla versus Cassandra in Memcache. So Scylla is handling the full traffic of 12 million requests per minute. Cassandra is handling actually only 500K. The other 95K is handled by Memcache. The average latencies of Scylla are around 4 milliseconds. The average latencies of Cassandra are around 8 milliseconds. However, there are spikes. And you can see them over here. The spikes here are due to Memcache not being able to handle all the traffic. So it doesn't have information for all the requests. And at times, Cassandra is hit by 1.7 requests per minute. And when that happens, the latencies spike up, and you're at 35 milliseconds response time. So to summarize, we reach a state where Scylla is handling more than 20 times the traffic at 100% better latency. And if we go back, Scylla is handling more than 20 times the traffic at better latencies than Cassandra. Once the Bursty clients issue was resolved, the question was, OK, now we know that Bursty clients are not in the network. Maybe that was the issue of Cassandra. And the answer was, let's try it out. So this was an attempt done 4 weeks ago, I think. And it was started by using consistency level of local 1, just to make sure that Cassandra won't crash. And Memcache was taken out. So Scylla and Cassandra are actually handling the full traffic, 12 million requests per second. And in this case, it seems that Cassandra is handling it fairly well. It's around 10 millisecond average latency. There are some spikes, of course. Please note that the maximum here is 80 milliseconds, while Scylla is at the maximum is 6 milliseconds. And we're handling the traffic somewhere between 2 and 3 milliseconds. OK, so Cassandra didn't die. Let's try to change it to local quorum and see what happens. So 3 weeks ago, this was done. And there was an attempt to drive the full traffic, again, after fixing the Bursty clients. And Cassandra is not able to handle the traffic. So the scale here is up to 200 millisecond latencies. And as you can see, Cassandra is handling the traffic at around 35 milliseconds And there are, of course, spikes much higher. Again, the SLA that we need to provide is under 10 millisecond latency. Regarding the Scylla, it's handling it somewhere around 4 milliseconds, as before. So the attempt to have Cassandra handle all the traffic showed that, at least with this setup of 30 nodes, it won't be able to provide the SLA that is needed. It really needs Memcache to front it, with all the issues that come along with it.
So, to summarize all the POC until now, we saw that Scylla is handling the traffic with better latencies. Now the current bottleneck is network. As shown before, we are using a 1 giga network, and the Scylla nodes are almost idle. Like, they can drink some mojito and relax. So I have the conclusions. What are we going to do? We are going to deploy a new cluster. We have a new data center at Sacramento. All the servers are connected with 10 giga network. We are going to use 3 nodes instead of 10 nodes. We are going to use larger disks because we are going to take all the data from 10 nodes and to reduce it to 3 nodes. So logic says more data per node. Also, more memory we'll put there. And if everything goes well, move to production. So a little bit about visibility. We have an open source project called Cassability. It's Outbrain's Cassandra Grafana dashboard. We are using Prometheus. And you are also more than welcome to use this open source and optimize it to ScyllaDB use. And that's it. Thank you, guys.